Hello, I just wanted to take a minute and talk a little bit about this vector diagram and the case we have here where we have a cannonball being shot out of a cannon at 20 degrees above the horizontal and how we create the vector diagram. So first thing to do is draw a little picture of what we have here. Here's the cannon and firing a cannonball at 120 meters per second and it's 20 degrees above the horizon. And now what we do is we draw a vector that represents that. And if you want to think about a vector as something that an arrow that starts at the beginning here and then goes up and goes at the appropriate angle and has a magnitude of whatever the amount is. So in this particular case, we can draw a vector here that represents the velocity of the cannonball. And we can move that vector then down separate from the little picture we have here. And now what we want to do is we want to create the components of this in the X and Y direction. And to do that, first of all, we have to kind of define what our X and Y directions are. So let's do that. Let's just pick the standard Y direction is up, and the standard X direction as to the right. And now what we can do is we can take this vector and we can create parts that fall along the X and the Y axes. And I've already drawn out a triangle here that kind of represents that. So we see here that we've got a vector in the X direction and a vector in the Y direction here that represent the sum of the vector in the X direction and the Y direction represent the vector in question, the 120. To get to the same place here, which would be this location right here, we can either go straight up this way or we can go in two parts. And we're going to do that. We're going to go in the two parts that we have that I've got listed here as velocity in the X direction and velocity in the Y direction. And those are the components. And what we're going to do is we're going to use some trigonometry to calculate what those are. So if we write an equation related to the ratio of the cosine and the sine and that angle, we'll be able to get those components. So we could say that the sine of 20 degrees, and remember that the sine is the opposite over the hypotenuse. So the opposite side is Vy, and the hypotenuse in this case is 120 meters per second. And let's leave the units off for a minute. And so if I solve this equation for Vy now, I have Vy is equal to 120 times the sine of 20 degrees. And you can plug that in your calculator and get an actual answer. And the same in the X direction. We can use the cosine of 20 degrees and the relationship there. The cosine of 20 degrees is equal to the adjacent side divided by the hypotenuse, and the adjacent side is Vx. So we can say it's Vx divided by 120. And then solving for Vx, we get the same thing in the cosine version, 120 times the cosine of 20 degrees. I didn't calculate what those were in advance here. First, I've got to make sure that my calculator is set on degrees. And then I type in 120 sine of 20, and I get 41.04. It looks like I only have, I don't know, one sig fig here, but I'll put 41 degrees or 41 meters per second for the Y. And then in the X direction, we have 120 times the cosine of 20 degrees, which my calculator says is 112.7. And I'll just round it off to 118. You can choose to do whatever you'd like in regards to significant figures here. A probably more appropriate answer for these would be 40 and 100, I guess, because it looks like we only have one significant figure. 20 degrees here, it's got one sig fig. But anyway, those are the answers. 41 meters per second and 118 meters per second, or oh, not 118, sorry. I read my calculator wrong. 112.8, which would be 113 meters per second. And you can round those however you want. Thanks.